pleased to welcome HGH Infrared Systems, and we have Catherine Barrett and Jérôme Duez, from both located in France. Catherine, if you'd like to upload your slides. Catherine's a graduate of the Institut d'Optique Graduate School and joined HGH in 1993. An expert in infrared technology, she's now responsible for 2 product lines at HGH, test and metrology and industrial thermography, which involves mastering the Kilnscan and Paris-Saclay IR technologies for rotary kilns. Catherine will be joined by Jérôme Duez, sales engineer at HGH and a Kilnscan and Paris-Saclay specialist. So, over to you, Catherine.
Thank you, Thomas, for the short introduction. Hello to everybody, wherever you are. So HGH is a more than 30-year-old company, and we are specialized in infrared technology. We've been manufacturing, testing, and measuring system for cement application and more generally heavy industry application since the beginning of the company 30 years ago. And especially the 2 systems that I'm going to present. And today I'm going to focus my speech especially on the kiln shell scanner and on the measurement of the temperature of the kiln shell. Actually, yes, our speech today is about the monitoring of the kiln shell temperature. And I'm going to demonstrate that this temperature monitoring is possible using the Kilnscan 23 system, whatever the kiln configuration. And yes, as Thomas said, Jérôme Duez, who is thermographic sales engineer at HGH, and I will be pleased to answer your questions at the end of this speech. So, thermography imaging systems are more and more used to monitor the temperature of critical areas for the cement manufacturing process. And as one of the pioneers in thermography imaging systems, HGH offers efficient support to the plant operators and control systems through the Paris-Saclay kiln and cooler camera. And you can see on the right here a few pictures extracted from the Paris-Saclay display. The first one here being from the kiln camera, and the other one for the cooler camera. And the Kilnscan kiln shell scanner system for monitoring the temperature of the kiln shell. What is the principle of the kiln shell scanner for rotary kiln shell temperature monitoring? So a kiln shell scanner is a line scanner measuring the temperature over one line along the kiln shell. And as the kiln is rotating, we thus obtain a full temperature image of the kiln shell, taking into account that the scanning speed is 25 Hertz, meaning that this line scanner measures one line 25 times per second. So thus, using the kiln rotation, we obtain a temperature map of the kiln shell. The angle of sight of the scanner is at least 90 degrees up to 140 degrees. Using this method, we are able to see the temperature of the kiln shell. This allows the operators to make the maintenance easier because it detects hot spots and measure brick and coating thicknesses. The benefits of the Kilnscan 23 line scanner are listed here. It ensures a long-term kiln shell integrity by a 24-hour, 7 days a week, real-time surveillance with alarms on critical parameters, with accurate and reliable measurements on temperature, thanks to its high resolution and its accurate temperature measurement resolution. It enables accurate maintenance scheduling through the monitoring of the evolution of the refractory status and the shell distortion by anticipating failures with preventive action and by minimizing downtime and optimizing maintenance frequency. The system is easily taken up by maintenance operator through its user-friendly software interface with visual results and intuitive parameter settings, and it is easily integrated into the control room and plant DCS. Going through the numerous installations we did all over the world, we faced multiple imaging challenges due to complex plant configurations. Among these complex configurations, the most frequent cases are illustrated here. On the left, the case of very long kiln for wet process, how to cover such long kiln. The case of kiln located inside a building with a short, limited free distance to locate the scanner, and which is actually maybe the most frequent case of challenging configurations, the kiln masked by posts and supports all along the kiln shell system plant. So this presentation is going to show you that our Kilnscan system remains well adapted even in those complex configurations. The first configuration regards the long kilns configuration. So the two lines, we have the possibility to integrate into our system two scanners located side by side and aiming at distinct portions of the kiln shell with an overlap, of course, of about 3 to 4 meter overlap to ensure seamless temperature measurement. In that case, the kiln shells, the kiln scanners are located approximately at a distance of the length of the kiln divided by 4. And this is, for instance, a typical configuration with two 90-degree field of view line scanners. There is a picture of such an application here in this plant. The two scanners are located at the top of a mast and they aim at two distinct portions of the kiln shell, each and the two images from the kiln shells are combined to create the complete kiln shell temperature monitoring. Another challenging case is when the free distance between the line scanner and the kiln shell is limited. In that case, we use our 140-degree field of view option so that the distance between the scanner and the kiln shell can be very short. As an example, for a 60-meter length kiln inside a building with a distance to walls less than 4 meters, we can integrate three scanners side by side, each of the scanners aiming at 1/3 of the kiln shell. This application, the case where such a configuration is installed, is frequently where when kilns are integrated into a building. We have such installation shown here in this building, where we have a very limited free space. We used a tilted 140-degree angle field of view scanner located just under the roof of this installation, and being able to scan all along the kiln shell without any loss of resolution. I mean, without any loss of spatial resolution and without any loss of thermal resolution. As regards the case of posts and pillars, they usually mask the kiln shell and they obstruct the field of view from the scanner, and they generate shadows. So we have to eliminate these shadows in order to see and to measure correctly the temperature of the kiln shell located behind. So you have such examples of frequent application shown here. Here we have posts supporting the tertiary air pipe, and of course behind the post we are not able to measure the temperature. Similarly, the post supporting the heat rock recovery unit may mask the kiln shell from the scanner. The principle of shadow elimination uses the combination of the images of two scanners aiming toward the same portion of the kiln shell, as for instance in this plant where two scanners are located in the blue cabins here. So as an example of this combination, and in order to demonstrate the image combination principle, I'm going to talk about the configuration of the Tasek kiln shell in Malaysia, where we installed 3 line scanner. So this kiln shell requires 3 scanners, all of them having up to 140 degrees field of view. The first one, the yellow with the yellow field of view here, the first one measures the temperature of the portion of the kiln located inside the building. That's why the distance between this scanner and the kiln shell is only 4.3 meters. The scanners 2 and 3 aims toward the same portion of the shell, and their images are combined to eliminate shadows. The example of this pillar, for instance, easily explains the method of shadow elimination. This portion of the kiln shell here is masked by the post here for the scanner number 3, while the scanner number 2 easily aims toward this portion of the kiln shell. So for this portion of the kiln shell, our system will take into account the data coming from scanner number 2. On the contrary, this portion of the kiln shell is masked for scanner number 2, while the scanner number 2 easily measures its temperature. So for this portion of the kiln shell, we will take into account the data coming from the scanner number 3. Here is the results on the display. So the first part of the kiln shell is covered by scanner number 1, shown in green here, while the second part of the kiln shell is a mixture of data coming from scanner head number 2 and scanner number 3. So depending on the location of the post and on the pillars along the kiln shell. And thus, then we obtain the image, the recombined thermal image for this kiln shell. And maybe you did not pay attention, but the junction between scanner number 1 and scanner number 2, somewhere here, is actually located on the thermal image here without any, and we can't see any difference. The signals and the measurements are synchronized, harmonized, and rephased to provide a single seamless thermal image of the shell. Last method of shadows elimination. Whenever there remain small areas which cannot be seen by the scanner head, plugging spot pyrometers into the system allows to monitor the temperature in these small shadow areas. So in that case, we can integrate up to 8 shadow pyrometers for the elimination of small size shadow areas, once again with seamless integration of data into the scanner image. So the Kilnscan system is a flexible solution, having met many challenges over the year. Whatever the kiln configuration, if it is for a new kiln or a revamping system, there is a Kilnscan solution, thanks to the multiple scanner configuration, well adapted for long kilns, thanks to our unique 140-degree extended scan angle, helping us to cover the full shell even in a building without any loss of resolution, thanks to the image fusion capability for complex shadows elimination, and thanks to the complementary pyrometers for punctual shadows removal. Thank you for your attention.
Thank you very much, Kathleen. That's very, very kind of you, and an excellent presentation on another invaluable piece of technology for monitoring the kiln shell, and for explaining the shadow elimination principle. It's possible to cover, like you said, any kind of kiln length, and regardless of the obstructions around it. And I think that's really important to understand. And given that there's probably people from over 100 countries logging into this call with all kinds of kiln configurations, I think you've covered all their requirements. There's a couple of questions. I wonder, in terms of you're able to cover the whole length of a kiln, and you're able to deal with the obstructions. One question is, is there any way of probably not of measuring directly underneath the tire, but is there a way of using the information that you have for the whole kiln profile to understand what might be happening to the heat profile underneath the tire? So that's obviously not in the view of the Kilnscan, but it's important because people need to know what's happening underneath. Is there anything that you can do in that respect?
Well, yes, the infrared imaging system does not allow to measure behind the kiln shell. There might be, however, some solution. Jérôme, can you please explain?
Yes, the question of measuring the temperature below the tire comes back frequently. Actually, there is no proper optical path to measure behind the tire, but we can do two things. First of all, there's usually a small shadow next to each tire, on each side of the tire. It is the projection of the field of view from the scanner. If the scanner is in front of one tire, there is almost no shadow, but for the other tires, you have some shadow. It can be 3 centimeters or 30 centimeters, so it can be more or less important. So first of all, we can use shadow pyrometers to monitor this specific area, and the signal is seamlessly combined in the full temperature map of the shell. But for monitoring really behind the tire, actually we'll not monitor the temperature, but we can monitor the tire slip. Since we are scanning lines and we need to synchronize them with the rotation of the kiln, we use a contact switch to know the rotation of the kiln. If we add contact switches, mechanical contact switches, very simple, to each tire, at each revolution, we know not only the speed of the kiln, but also the speed of the tire. So we can monitor and trend the gap between the shell and the tire. If the kiln is getting hotter just below the tire, it will expand, reducing the tire gap and tire slip, so that by monitoring the tire slip or tire gap, we can get a warning if the temperature increases just below the tire.
Okay, thank you very much. That's really useful explanation. And I guess when we see the profile in those pictures, Catherine, is that it taking into account the estimations, and is it integrating information for what it assumes or estimates is the temperature behind the tire?
Yes, the contact switches data is of course integrated into our process, and the monitoring of the tire slip is integrated into our system. So this information, the tire slip monitoring, giving information of the temperature behind the tire, is integrated into our system. Yes.
Very good. One question that seems to come up a lot is calibration of the Kilnscan. How is the calibration carried out?
The Kilnscan system is a very stable and reliable system. Anyway, we recommend the calibration approximately every 2 years. In that case, there are several possibilities. Yes, the simplest one being to ship us back the scanner for calibration, and we send the calibration back to the cement plant. This can be, of course, done during the stop of the plant. So this this calibration process is very short. So the new calibration parameters are then uploaded into the software managing the Kilnscan system. And another solution, if in case that the system, the line scanner cannot be removed and shipped back for calibration, is that we replace the sensing unit directly on site by a freshly calibrating sensing unit with its own calibrating calibration parameters.
Okay, very clear. Thank you very much. Just in terms of how the data is then integrated into the plant's overall control systems, how is that done, and how difficult is that to accomplish?
I let Jérôme answer to this question. Maybe you know better than me.
Yeah, for integration, we have different possibilities. First of all, on the analog way, we have relay output contacts that can activate. We can close contacts when an alarm is triggered, so that it can be used to run a fan, for example. We also have 420 milliamps outputs to share temperature information. But the best option is definitely the digital OPC protocol to share maximum of information with the control system. So it can be temperature values on given areas, or also the status of alarms.
Okay, very good. In terms of the kind of measuring temperature, what about the environment and the kind of atmosphere, moisture? How do they interfere with the measuring of the temperature?
Because of the distance between the kiln and the scanner head, so it can be 30 meters, for example. Indeed, the atmosphere conditions can affect the measurement. If it is snowy, for example, the radiation received by the sensor will be reduced, so the temperature would appear lower than what it is actually. So one solution for this is to install a pyrometer very close to the kiln, and we will use it as a reference. Since it is very close to the kiln, it is not affected by atmospheric conditions. So the scanner will compare what it sees with what the pyrometer sees, and then we can compensate and correct the temperature information of all along the kiln with this system.
Okay, yeah, thank you. And just quickly, if you have 2 to 3 pyrometers installed, is the increased measuring angle, is it changes the accuracy at all, or are you very confident in the uniformity of the measurement?
Actually, when the measuring angle is big, so we can scan up to 140 degrees, the spot size will vary. When in front of the scanner, the spot size is a circle and is the smallest. But when looking at the end of the kiln, the spot size is getting bigger because of the distance and also because of the angle. So this will create some kind of averaging effect because the spot we are measuring is bigger. But since we have a very good spatial resolution, the spot is very small, even at the end. So the averaging effect is not very important. It's still about the size of one refractory brick. So we can still detect the failure of the first brick.
Okay, very good. Inevitably, what is the cost of a scanner or payback time? Is there any indication you can give for the investment required?
Payback time can be really quick because it's difficult to say about prices because as we have seen in the presentation, every kiln is different and we can use 1, 2, 3 sensors. So the price will not be the same, of course, accordingly. But a relining of the kiln is really expensive, much more expensive than the scanner.
Yeah.
So optimizing the stoppage dates and relining schedule is definitely something you can do with the scanner. So price is almost nothing.
Yeah. Yeah, no, I point taken, and thank you very much for answering those questions and for a great presentation and another invaluable piece of technology that I know that people rely on, and it's a great asset for any cement plants. Thank you both very much, HGH from France, for participating in the webinar.